To do this work then, we went back to the site of the original tracer experiment at Canadian Forces Base Borden, and here's the source region for the original experiment, and shown schematically here a sort of maximum extent ball for the perchloroethylene plume after about 2 years. Now, I didn't mention previously, but I should now, why are we looking at perchloroethylene in all of these experiments? It's a chlorinated solvent, and of course it's one of the most frequently detected of the chlorinated solvents in groundwater. It's been used in degreasing and dry cleaning operations and inadvertently released in many situations, so that it's a relatively common and important contaminant that has a very low drinking water standard. So here's the original plume. Now, my former advisor has done experiments here subsequently, and there are many other chemicals that now exist in this region of the groundwater system, and we didn't want to study the geochemistry of that, so we marched over here to a clean zone of the aquifer and collected 11 cores covering 10 meters of the aquifer at the same vertical depth that the original contaminant tracer experiment was conducted. That's about 1.5 meters to 3 meters below the groundwater surface, or between the ground surface, about 0.5 meter below the water table. The first thing that we do is map lithofacies, and the types of features that we're using here are the standard parameters that sedimentologists use to map any kind of sedimentary aquifer. That's grain size, sorting, laminations, distance between laminations, angle of the laminations, and so on. And by that mapping then, we produce descriptors like these: massive coarse-grained, distinct plane laminated, massive fine-grained, and complex cross-stratified. And you can see here how within our distinct plane laminated facies, the laminations are highlighted by higher concentrations of dark minerals, including magnetite, and how much better sorted this facies is compared to this facies, which is very poorly sorted and much, you can't tell really, but it is much coarser grained than the other one. So these are the kinds of variations that we see. You might think of these, if you map larger sedimentary systems, as sort of micro facies mapping, but the scale at which we're mapping here, using the same kinds of descriptors that are standard, is appropriate for the plume scale variability that we see in this aquifer. The next thing that we do is we measure the permeability using an air permeameter. We dry the samples, take subcores of our cores, dry those samples, measure using an air permeameter the air permeability, and we can convert that to a saturated hydraulic conductivity. And then we measure the sorption distribution coefficient. Again, for PCE as our probe compound, we seal a sample of the Borden sand, water, a known mass of PCE in one of these vials, allow it to equilibrate between phases, then we can divide the sorbed concentration by the solution concentration, and that gives us our sorption distribution coefficient, or the KD. And remember that the retardation factor is a function of the sorption distribution coefficient, and that as KD becomes larger and sorption becomes greater, the retardation factor also is expected to become larger. And this is the kind of two-dimensional map that we get for the sorption distribution coefficient. And we're looking here now at 1.5 meters, the same vertical interval over which the test was conducted, and 11 meters or 10 meters horizontal. These are our 11 cores. One of our cores is at each one of these numeric marks. The scale goes from lower to higher, and each increment of color corresponds to one increment of variance of the distribution. You can see that the distribution is actually non-normal with your eye, and that it's actually skewed left, that is with a tail on the right, and that the high values occur just here in a couple of layers, here and here. So you've got kind of a sea of gray or coral pink with just a few high zones of high KD in it, and that has important implications for contaminant transport. What I want to do now is a thought experiment. And what I want us to do is to reverse the information compared to what kind of information we've had before. So leaders in the field, when the early experiments were done, collected, in fact, a great deal of information on the variability of the permeability field, and there wasn't as much information on the KD field for the organic contaminants available. And so one of the things that's been done in modeling studies to try to understand how important heterogeneity was to use the known variability of the permeability field and imply something about the variability of the KD field and run experiments and try to understand what's important. Let's pretend that we don't know what the variability of the permeability field is, that we only know the variability of the geochemical parameter, our KD. And so we'll assume that the permeability is uniform, but that we know the geochemical variability. And let's do a little experiment where we think about running a tracer through this system. So the tracers would be at the upflow side, we put in chloride and a PCE solution, non-reactive and reactive tracer, and we measure them in a depth integrated fashion at the outlet end. Well, for the chloride, what's going to happen as groundwater flows through this system is that we get relatively little dispersion of the chloride because the permeability field is uniform. And because I did calculations using an approximately 10 centimeter per day velocity and a 10 meter long flow field, it takes about 100 days for the chloride to elute from that column. But it's a little more complicated for the PCE then if we overlay the variability of the distribution for the KD that we know we have. And now what I want to do is just have you think about what happens in different horizontal zones of this sort of 2D column. If PCE were to travel with chloride through this zone, we'd see just a little bit of retardation, wouldn't we? And we might get a graph that looks like this so that we see PCE retarded a little bit compared to the chloride because there's a little bit absorption of the PCE along this flow path. But if we look at the zone just above that, in fact, we capture that lens of the highest absorption. And now that would cause a greater retardation of PCE in that zone, although the chloride behavior would be no different. And in fact, what I've done here is to schematically show a little bit greater retardation of the PCE, but it should be out here. So if we think about all the different layers that could be carved into this 2D system, what we end up with is, at the end of our thought experiment, a breakthrough curve that might look something like this, which has a very long tail on it for the PCE. That is that we've got a lot of dispersion of the reactive contaminant compared to the non-reactive tracer because of the geochemical heterogeneity, because of the distribution of the PCE absorption coefficient in the system. And that is a geochemical reason for plume dynamics being caused by geochemical heterogeneity, devoid of physical heterogeneity. To recap, then, the lenses of high absorption can result in enhanced plume scale dispersivity for the reactive solutes compared to the non-reactive solutes. Now, we still need to test that more quantitatively by running some more rigorous modeling studies with this information in mind. But you can see that, I hope, there's a reasonable set of data that's consistent with the hypothesis that we put forward. I want to talk for just a couple of minutes about what let me show you the distribution of permeability, because we did measure it. And now down here, in blue shades, we've got the permeability distribution that we measured. Again, darker are higher values, lighter are lower values. Each shade that we show here is one increment in the variance as well. And it turns out that the variance for LNK is the same as the variance for LNKD. So by one measure, we've actually got some similar characterization of the distribution of these properties. The KD is as variable as K in some measurement. But in fact, when you look at the two fields, you find that the patterns are very different. You don't see a direct correlation between the variability in the LNK with your eye and the LNKD. So what kinds of correlations might be appropriate between these two fields? These are the two things that we need to know to model contaminant transport for this contaminant in the groundwater system. I think that we can learn a lot by looking at the mappable lithofacies. So what we've done in our study is to plot up the cumulative distribution function for each of the lithofacies and for each property. So for example, here we take all of the measurements of permeability that we have for the massive fine-grained facies, and we just stack them up lowest to highest, make a cumulative distribution function. And we've done the same for all samples from the 11 lithofacies that we've measured. And when we test for significant differences between those distributions, we find that we get 4 relatively distinct groups. And so what I've done is to pull out one example from each of the 4 groups to show you what they look like and how they differ. A few features that I think are interesting and useful. We get nice, relatively S-shaped distributions for each of the lithofacies groups, which means that the distribution is relatively symmetrical. The slope's approximately the same for each of the lithofacies, and that means that the variance for each lithofacies is about the same. And they differ primarily by the mean value. So we've done a little bit more sampling by taking some additional cores in the opposite direction compared to the direction of flow, and doing the same kind of exercise, comparing the new distributions that we get to the old, and we get almost bang on the same results for 9 of the 11 lithofacies. And for 2 of them, they're a little bit different in ways that may be important and interesting, or maybe just because we don't have enough samples to define the distributions as well as we should. But what that suggests to me is that, in fact, this information can be used in a predictive way within this aquifer, that if you had this kind of a characterization for a distinct plane laminated facies and you had a good map of where those facies exist within the aquifer, you could populate it with this kind of information quite easily. Let's look at how the sorption distribution coefficient is correlated to lithofacies. It is, but now you can see that the Z, which is the silt facies, which was on the left side, has now moved to the middle of the pack. And now, instead of seeing primarily a difference in the mean value, you see primarily a difference in the slope. So what we find is that, again, there are significantly different properties associated with groups of samples from the lithofacies that can be used in a predictive way, we think, but that they're different from the groups that we got for the permeability. So here we get 3 groups, a distinct plane laminated. It shows one of the groups. These 2 demonstrate the middle group, and the massive coarse grain demonstrates the other group on the right-hand side. So what we learned from this is that we find that both the permeability and the reactivity properties are correlated to our mappable lithofacies, but there isn't a direct correlation between these 2. Now, this is important because often when we've got this information, we tend to want to make a direct correlation between those 2 by saying, okay, permeability is correlated in some way to grain size and surface area, and so reactivity must also be correlated directly to that. But reactivity, remember, of any kind is going to be correlated to the reactive surface area for whatever reaction you're interested in. And the sorting that you saw in the sediments, just the variation in color, tells you that the material properties of those sediments varies. So in fact, the trends that we see, I think, are explainable by the fact that we're averaging different types of information when we're looking at these 2 different properties. Because the mappable lithofacies tell us about the sorting of the sediments with respect to each of the properties we're interested in, this is useful, but we shouldn't be making direct correlations between these 2.